Alright guys, so we are finishing up with stoichiometric relationships this week. Finally, I know we've been on it for a long time. Part 3 is really actually pretty short. We're actually going to finish it up today. Part 3 focuses on solutions. So part 1 focused on kind of all solids and doing molar mass calculations and Avogadro's number and all the general stoichiometry stuff. Part 2, then, we focused on gases. We did the gas laws. We talked about the molar volume of gases at STP and how all of those different things fit into stoichiometry. And so part 3, we are focusing on solutions. And so we're going to be talking about dissolving substances in water and making solutions and dealing with concentrations of solutions, how to calculate the different concentrations, and then how that kind of plays into doing stoichiometry. And so this is really important because a lot of our chemicals, they are not going to be in a solid form or sometimes even a gas form. A lot of times, especially for ionic compounds, they're going to be dissolved in solutions. Same things with acids and bases that we get to later on in the year. And so it's really important to know how solutions fit into stoichiometry because they're going to be very important as we go through the rest of the class. So just to kind of start off with the main parts here, obviously we need to know what different concentrations are. The most important one we're going to deal with is the molar concentration, which is called molarity, and we'll get to that a little later. And then we also need to know what's called a standard solution. That's typically what we make in the lab, where a standard solution is where we have a known concentration. And so sometimes they're called stock solutions because they're what we usually use in the lab. And you can dilute them down and make different concentrations from them. But it's kind of an important thing to know. We need to know how to solve problems here. So it says involving molar concentration, so that's that molarity, the amount of a solute, which is moles, and the volume of solution. And then actually this is not in our notes here, but we are going to get to this in a kind of a separate area. But there's an experimental lab technique called a titration. And the titration actually uses concentrations of solutions in order to do some calculations and determine some things. And it's actually a very important lab technique that can be used in different ways. And so we'll be covering that later on this week. So kind of some basic definitions here to start off with. We need to know kind of what are solutions and what are the parts of them. And so if you think back all the way to the beginning of topic 1, we had talked about homogeneous and heterogeneous mixtures. And so the term solution is kind of a synonym for homogeneous mixture. And so if you hear the term solution, solutions are homogeneous mixtures. And so solutions, typically they follow this pattern where they have two parts to them. They have a solute. Most likely that's going to be a solid. It can be a gas. If you think of like soda is a solution and the solute in there, one of them is a gas. You have your carbonation, your bubbles. But most of the time in our solutions, solutes are typically solid. Things like salt, things like sugar, things like our other solid chemicals that we can dissolve into water. The other part of a solution is called a solvent. I would say 99% of the time, the solvent is usually water. And that's because of all the unique properties that water has. It's a polar molecule, so it can dissolve ionic compounds. It can also dissolve polar covalent compounds like sugar. And other things like that. And so typically when we're talking in chemistry, most of our solvents are usually water, and our solutions are what we call aqueous solutions. And if you see me write SOL''N, that is the abbreviation for solution. Okay, so if you're somebody who likes to write shorthand, that's a good shorthand thing to remember for writing your notes. And so here's kind of a visual example. We have salt, which if it's table salt, then that would be sodium chloride. It doesn't have to be sodium chloride. Remember, salt in chemistry is a generic term. Salt is any ionic compound. So if, table salt is NaCl, that's the most common one that we usually think of. Our solvent is water, so we have H2O. And when we mix them together, we get a solution, and that solution is salt water. So remember that when we dissolve things, this is a physical physical change. Dissolving something is not chemical. A lot of people confuse that, but the solution is still going to have the same properties as the two separate things from when it started. So the salt had kind of its own unique taste and its own unique properties. The water had its own unique properties. And afterwards, the solution of salt water, it retains all those individual properties. The salt dissolves, and so it looks like it kind of disappears, but that's not chemical. That is just physical. Okay. Solutions, you can dilute them. If you dilute something, that means that you are adding less solute and more solvent. If you want something concentrated, you're going to increase the amount of solute. So if you think about, if you like to make like Kool-Aid or lemonade, the concentration, like what taste you like, is maybe going to be dependent on your taste buds. So maybe you like it concentrated, so you're going to dissolve more of the Kool-Aid powder or more of the lemonade powder into the same amount of water. But maybe somebody else that doesn't like it as sweet or as concentrated, they're going to dissolve less of that powder in the same amount of water. And so concentrated and dilute are terms that just indicate that we're going to have more or less of the solute particles in the solution. Okay. This next part is just kind of a crash course of something that's kind of related to the lab stuff for the class. And so standard solution, I kind of mentioned it at the beginning here. It's a solution that has the concentration that's already known accurately. So a primary standard solution, it says, is prepared using a substance of high purity, and it's dissolved in a known volume of solvent. And so there is a very, very specific technique that you use to make a standard solution that typically we would be doing in the lab part of this class. We may have to kind of come up with some other options for that. I may have to kind of video myself doing that to show you guys, or find another video example of that. But knowing how to make a standard solution, that's a really good technique to know for chemistry, because you want to make sure that you have an accurate concentration so that when you're doing your experiment, you get correct results to analyze, and you're not going to have data that's thrown off because your initial solution wasn't calculated correctly. You can also have what's called a secondary standard solution, and this is one where you determine the concentration through a titration, and I mentioned that word earlier. And so we're actually going to be looking at that later on this week or next week, where we have a solution. We have a primary standard solution that we know the concentration of it because it was made and determined accurately by somebody. And then we can use that primary standard solution with a solution that we don't know the concentration of, and we can determine the concentration of that solution. And so we're going to talk about how we do that next week, because it does involve some math, but it involves a lab technique and measuring some data and some volumes. Okay. And then it kind of just says here that when making a standard solution, it's important that we have the correct mass of the substance. So when you're measuring it on a balance, it needs to be very, very accurate. And you also need to make sure that all the solute is transferred into your volumetric flask. If all your solute doesn't get transferred, then technically your calculation for that concentration is not going to be accurate. If some of the solute sticks to your little weighing dish and it doesn't get into the flask, or it sticks on the sides of the flask and it doesn't get down into the water to dissolve. So when you're making those are some errors that could happen if your balance is off and it doesn't measure the correct mass, or if you don't transfer all of that solute into the flask that you're trying to dissolve it into the water. So kind of the second big part of this is just knowing how to calculate concentrations. There are various ways that you can calculate concentrations. The main one, like I said, is going to be what we call the molar concentration. And so a lot of times you will hear it referred to as molarity. And that is this equation right here. The molarity is the concentration where it is moles per cubic decimeter. So it's moles of solute, amount of solute in moles, divided by the volume of the solution, and it does have to be in cubic decimeters. So remember, if they give you cubic centimeters, which happens a lot because our graduated cylinders in our labs, they measure in milliliters, which is equal to cubic centimeters, okay? So a lot of times if we're getting data from a lab, the volumes will be in cubic centimeters, and we're expected to know that we needed to divide that by 1,000 to convert it to cubic decimeters. So keep that in mind. That's very, very important on some of your practice problems. You're going to be given cubic centimeters, and you're going to need to convert it first before you do anything with it in the calculation. Okay. You can also calculate concentration, as it says right here, with grams per cubic decimeter. That is less common. The vast majority of the time, we will be using this one with the moles and cubic decimeters. I would say probably like 99% of the time, but it is good to know these other two. And the one is the grams per cubic decimeter that I mentioned just a second ago. The other one is called parts per million. This is what they use a lot in sort of environmental type things. You'll hear people measure, they'll say, oh, that's so many parts per million. And they're determining maybe whether the water is safe to drink because of the chemicals or the minerals that might be dissolved in it and things like that. And so their two equations are given here. The one with the grams per cubic decimeters, it's very similar to the molar one. The only difference is it has the mass of the solute in grams at the top instead of moles. The bottom is still the same though. It's the volume of the whole solution in cubic decimeters. The parts per million one is the one that is a little bit different. It has the mass of solute in grams on top, but on the bottom it doesn't have a volume. It has the mass, but notice it's the mass of the entire solution. So the solution, that means it's the solute plus the solvent. So on problems that involve asking you to do parts per million, make sure, and I'm going to rewrite this because I didn't write it very nice the first time, but make sure that if you're asked to do the concentration in parts per million, that for that denominator value, the mass of solution, you have to add the mass of the solute and the solvent together. So if they say, oh, you dissolve so much of this chemical in so much water, you would need to add those two numbers together, those two masses for that equation. And then, since it's parts per million, you actually do need to multiply it by some scientific notation, and it's times 1 times 10 to the 6th, okay? But again, these two we're not going to see as much as we're going to see the molarity, and so that's the one I'm going to focus on kind of here at the beginning. If I'm calculating the concentration, I use C, and if it's concentration with the moles, the molar concentration, then it's going to be the number of moles, the amount of moles on the numerator, divided by the volume, and it's the volume of the solution in cubic decimeters in the denominator. Now, I may need to rearrange this. They may give me the moles, and they may give me the molar concentration, and they ask me to solve for volume, so it would look like this. They may give me the concentration and the volume and ask me to solve for the number of moles. This one they do a lot because they will actually ask you to solve for the mass, the number of grams of the solute that was dissolved. And if they do that, then typically you use this equation to solve for the number of moles. And then you look at the chemical formula and you use the molar mass to then convert moles to grams for that final answer. And we're going to take a look at an example like that a little bit later. So I'm going to go through some examples now so that you guys have some to refer to when you are working on your own. This one, it says we have 50.0 grams of sodium chloride, and we are dissolving it in 100 cubic centimeters of water, okay? And so I want you to kind of get in the habit of thinking, okay, this is the solute, because it's saying we're dissolving it, and we're dissolving it in this water, so that is the solvent. So like we said earlier, water is almost always the solvent. So that's how I would kind of think about that in my head, is that the sodium chloride is the solute, the water's the solvent. But I want you to pay close attention, because then over here it says, and then that's made up to 500 cubic centimeters in a volumetric flask. So what they are doing is they're telling you that 500 cubic centimeters, that is the total volume of the solution. So this 100 centimeters of water, that's actually kind of extraneous information, okay? And the reason is because, yes, you initially dissolved it in 100 cubic centimeters of water, but then you increased it all the way up to 500. So 500, that's my number that I would want to use for my total volume of the solution, okay? So just be careful when you're reading if they do something like that. So then this question says calculate the concentration of the solution, and they want us to do it in both the molar concentration and with the mass, the grams per cubic decimeters, okay? And so I'm going to do the molar volume first, because that one is going to take a little bit extra time, because they did not give us the number of moles. They gave us the mass. They gave us this 50 grams. And so the first thing really that I would need to do is I need to figure out what's the molar mass of NaCl, because I need to convert those grams to moles before I can put it into this equation that we have up here. So we're going to use this equation, but we have to convert the grams to moles first. So NaCl is pretty easy. So I have Na, which is 22.99 on the periodic table, and I have Cl, and I don't need to multiply either of them because they don't have any subscripts. So Cl is 35.45. So I'm simply going to add them together, and I end up getting 58.44 grams. Now, the reason that we did this is because I need to take that 50.0 grams that they gave me. Let me rewrite that a little bit neater. That's the grams, the mass of the solute, but I need to convert it to moles for the calculation of the molar concentration. So if I want to convert grams to moles, I put the molar mass here on the bottom because I want those grams to cancel out. Okay. So that cancels out, and then I have 1 mole on top. So all I'm doing essentially is dividing here. So 50 divided by 58.44. And because this 50 was 50.0, that's 3 significant figures. So that means I want my answer to have 3 significant figures. So when I do 50 divided by 58.44 and I round it to 3 significant figures, I get 0.856 moles of NaCl. Sorry, my mole is a little messy there, but that's MOL. So that's the number of moles, but I'm not done yet because that's just the N. Okay, I still need to calculate the concentration. So I'm going to erase this so that I have a little bit more room over here. Okay. And so now I need to actually calculate my 2 concentrations. So I'm going to do the molarity one first, since that's what we just got the moles for. So the concentration, and this is the one for moles per cubic decimeter. And so this is the number of moles over the volume of the solution. The number of moles we just calculated is 0.856. Now the volume, okay, the volume on the bottom, in the problem it's 500 cubic centimeters. But I told you guys up here, the volume has to be in cubic decimeters. So a lot of times they will give it to us in cubic centimeters. We need to divide by 1,000 before we plug it into that equation. Dividing by 1,000 is really easy, okay? If I have 500.0, I divide by 1,000, that means I'm moving my decimal place 3 places to the left, okay? So anytime you divide by 1,000, that's what you do. Just move the decimal place 3 places to the left. That's an easy shortcut trick to save time. If you were multiplying by 1,000, you'd move it 3 places to the right, the opposite way. But since I'm dividing by 1,000, I know that 500, that is going to change to 0.5000, and I'm going to keep all the zeros just because I need to look at my sig figs when we divide this. So 0.856 divided by 0.5, and I need to round to 3 significant figures because this number has 4, this one only has 3. So when I round my answer to 3, I get 1.71. And then I always want to make sure I put my units, which is moles, and then it's times decimeters to the -3. Now, remember that IB doesn't like units in the division, so that's why they have it written as moles times decimeter to the -3. Because really, if we go back up and look at this equation, okay, if I kind of clear this off a little bit right here, the units are moles per cubic decimeters, but IB doesn't like units in the denominator, and so they have done the inverse, and so they're going to say it's moles times decimeters, and then it'll be to the -3 because we are moving it up to the numerator. So keep that in mind. That's why that has that negative sign there. Now, the second part they asked us to do was the concentration where it was the grams per cubic decimeter. That one's actually a little shorter because we already have the mass in the problem. So we have the 50.0 grams. And then the volume, again, I do need to make sure it's cubic decimeters, so I'm going to use that 0.5 again after we divided it by 1,000. So if I do 50 divided by 0.5, I get 100 grams per cubic decimeter. And really, I should put a decimal here at the end of the 100, and the reason for that is because, again, this 50.0 is 3 sig figs, and so if I just write 100 with no decimal, that's technically just 1 significant figure. So that's how you do a couple of those. I'm going to kind of skip down here Your practice exercises that you are responsible for doing for your grade are going to be these 2 pages, but I'm going to go through, or actually 3 pages, sorry. But I'm going to go through and do an example on some of them because we didn't have all of them in this example I just did. So I'm not going to do any on number 1 because number 1, all 3 of those are exactly like the one that I just showed you, okay? I'm going to do one here from number 2. And the reason I'm going to do this one is because this one, we're still using concentrations, but they're asking us, if you read it, they're asking us to calculate the amount in mole, okay, of the solute. So if you go back up to our information up here, we would be using this equation here, the number of moles, okay? And so we're going to be multiplying the concentration, the molar concentration specifically, times the volume in cubic decimeters. So on number 2, if I read, they give me the volume, and notice it's already cubic decimeters, so I don't need to convert it. If they give you cubic centimeters, for example, like letter B and letter C both have cubic centimeters, so on those, you will have to convert to cubic decimeters first before doing your math. And then they give me the concentration, they give me the molar concentration, it's 0.4 moles per cubic decimeters, and they tell me that it's ammonium chloride. They don't give me the formula. But you guys should know because you did learn how to write chemical names and formulas last year. And so this is an ionic compound. Ammonium is NH4 with a positive 1 charge. Chloride is Cl with a -1 charge. And so if I put those together, I just need one of each to balance it out. And so ammonium chloride is simply NH4Cl written together like that. So, doing my equation from up there, I know to solve for the number of moles, I'm going to do the concentration times the volume. And since both of these numbers are already correct in the units, I don't need to convert any of them. I can just go ahead and plug them in. So the concentration is the 0.4 moles per cubic decimeters. And the volume is 0.250 cubic decimeters. So if I multiply these, 0.4 times 0.25, and I want to keep my answer to 3 sig figs because both of these numbers in the problem have 3 sig figs, so that's the least. So if I multiply them and keep it to 3 sig figs, I get 0.100, and since I was solving for the number of moles, it's 0.100 moles of ammonium chloride. So that's where that NH4Cl comes in, because I'm going to just make that my label here at the end. So that's pretty straightforward. B and C will be the same. The only difference is that, like I said, they give you the volumes in cubic centimeters, so you're going to have to divide those by 1,000 before you do the actual calculation. Number 3, it's really similar to number 2. In fact, it starts out the same way. I need to solve for the number of moles. But then if you read, the question asks you to calculate the mass of the solute. And so after we do kind of like we did on number 2 and get the moles, we would then need to use the molar mass of the substance to change it and convert to grams. So I'm going to work through letter A on this one so you guys have an example to refer to. So let me switch colors here. Again, my volume is cubic decimeters, so I don't need to convert it, but on B and C, you will need to convert those. And so I'm going to start off the exact same way, N equals, and I'm going to plug in my concentration is 0.200 moles times decimeters to the -3. And then I'm multiplying by that volume, which was 2 cubic decimeters. So if I multiply those and I keep my answer rounded to 3 sig figs because both of these numbers in the problem have 3 significant figures, I get 0.400 moles, and it's moles of potassium hydroxide. It's KOH, tells me right here what it is. Potassium hydroxide, KOH. So that's the moles, but I'm not done because in these problems it asks for the mass. So there's going to be a second part to these. So I'm going to kind of erase this, and then we'll go back and do the second part. Now the second part is going to involve the molar mass. I know that I have 0.400 moles, but I need to convert those moles to grams, so I need the molar mass. I know 1 mole equals a certain number of grams, so I'm going to come over here to the side, and I'm going to go, okay, KOH, And I'm going to look up on the periodic table. Potassium's mass is 39.1. Oxygen is 16. Hydrogen is 1.01. So I get 1, that's 16, I believe. 3, 4, and carry the 1, 5. So 56.11 grams is the molar mass. And so that number is what I just take and put up here. And then from there, it's just multiplying. So 0.4 times 56.11. And I want to keep 3 sig figs again because that 0.400 was 3 sig figs that I'm starting with. And so when I multiply those and then round to 3 sig figs, I get 22.4 grams of KOH. And that is actually the final answer on that one. So B and C are exactly the same way. Again, it's just make sure you're careful of your volumes. They're both given in cubic centimeters on that one. So you will need to convert them before doing your calculation. This second page has a lot of different parts per million exercises. And so just briefly, I wanted to kind of go through these. So just as a reminder, if I kind of go back up here, parts per million is the one that is slightly different in the denominator. It has the mass of the solute here, but in the bottom it doesn't have a volume. It has the mass of the solution. And remember I told you that that includes the solute and the solvent being added together. And then you multiply by 10 to the 6th before your final answer. So that's going to be the equation that we would use for these that they ask for parts per million. So this one, if I read, it says I have 25 grams of a chemical and it's dissolved in 75 grams of water. We'll calculate the concentration and it says in parts per million. Okay. So again, I want you guys to get in the habit of thinking, okay, 25 grams of a chemical is dissolved in a certain amount of water, so whatever is being dissolved, that is the solute, and whatever's doing the dissolving, which like we said is pretty much almost always water, that is the solvent. And so when you set this up, okay, I'm doing the concentration, and I'm doing the parts per million one, and I need the mass of the solute, which is 25 grams. But then the bottom, I need the mass of the whole solution. And so that's the solute and the solvent together. And so in this one, that's 100 because I have 25 grams of the solute and 75 grams of the solvent. So on the bottom, I'm actually going to have 100 grams for my total mass of my solution. And then I would multiply by 10 to the 6th. So in your calculator, you would do 25 divided by 100, which is going to come out to 0.25, okay? And so you would get 0.25 times 10 to the 6th. And then if you want to fix that for correct scientific notation, I would have to move the decimal once, and that would make my exponent go down. So my answer would be 2.5 times 10 to the 5th parts per million. Or if you wanted to write it out and not in scientific notation, it's 250,000 parts per million, 250,000. But scientific notation is probably better because it's a large number. So that's how you would do the rest of them in this section. Again, just be careful on that bottom, that denominator, because the solute and the solvent usually add up because the total should be, from the bottom, should be the mass of the solution. Okay. This last page, this actually starts taking concentrations, our molar concentrations, and applying them to stoichiometry. So this is kind of where this fits in with the rest of stoichiometry. We can actually use the molar concentration as a conversion factor. So when we have solutions in our reactions, this is where we use their concentrations. So if I read this one, it says, what volume of this molar hydrochloric acid reacts completely with 5 grams of magnesium? So there's two parts to this one. It asks me first, what volume, let me switch back to orange, what volume of this concentration of hydrochloric acid reacts completely with 5 grams of magnesium? And then it asks me a second part. It says, what volume of hydrogen gas will be produced at STP? So there's two parts to this. So I'm going to go through the first question first, and then we'll address the second one after that. So they've given me a balanced equation here, and I can see everything. And so since they're asking me, I'm solving for the volume, right? The volume of hydrochloric acid. I'm going to start with this. This is my given, okay? So I'm starting with 5 grams of magnesium. And I know from doing all my stoichiometry that if they don't give me moles, the first thing I always want to do is convert to moles when I'm doing my stoichiometry map. So since I have grams and this is a solid, I'm going to use molar mass, which is from the periodic table. Magnesium should be, I believe, 24.31 grams per mole. And then I always want my molar ratio in here. So the molar ratio that we need is the one for magnesium, which is right here, to the other reactant, which is hydrochloric acid. So if you look at their coefficients, that is a 1:2 ratio because the Mg is 1 mole and the HCl has the 2 coefficients. So that's 2 moles of HCl. Now, this last box is where this is going to be slightly new because they're asking us for the volume, okay? And this is not a gas. So in part 2, anytime they asked us for a volume, if it was a gas, we use that 22.7 cubic decimeters, right? Well, that's only for gases. That does not work in this section for solutions. So if you're asked to solve for a volume of a solution, you're going to have to use the concentration of the solution. And so they gave us that in the problem so that we could use it. They told us that it's a 2 molar solution. So what that means that it's 2 moles of HCl for every 1 cubic decimeter of HCl. Okay, that's what molar concentration means, or for solutions. It means that you have that many moles per 1 cubic decimeter. And so you can turn it into a conversion factor, just like I wrote in this last box. Okay, and so now it's just a matter of doing our math like normal. So I have 5 divided by 24.31 times 2 divided by 2. So really these 2's are going to cancel each other out. And so really you just need to do 5 divided by 24.31. And so when I do 5 divided by 24.31, I should get 5 divided by 24.31. And then if you want to multiply and divide by the 2, you can, but that's not going to change the answer because they're going to cancel out. And so that's going to give me, and I want to round it to 3 sig figs because this 5.00 I started with was 3 sig figs. That's going to be 0.206 cubic decimeters of HCl. And so if I wanted to do this reaction, I would measure out that volume of hydrochloric acid, and then I could react that with this mass of magnesium, and it would react completely. Okay. Now, the second part of this is then what volume of hydrogen gas is going to be produced at STP. So they're kind of combining topic 2. This is how everything kind of fits together. So you can see that, we had a molar mass here, which was from part 1. We have our molar ratios. We have this concentration, which is the new for this part 3. But then the second question is asking about us about the volume of a gas at STP, and that's from part 2. So all of these things are going to start kind of intertwining now. We're going to have gases, we're going to have solutions, we're going to have solids, and so it's all kind of a lot, and so you just have to make sure you're paying attention to what it's asking for so you know the correct way to set it up. So I'm going to clear us off here and set us up to do that second part. You finish erasing everything. All right, so then our second part is what volume of hydrogen gas will be produced at STP, okay? And so on this one, I'm going to start with that same, my same 5 grams of magnesium, okay, because that was my given. But now I'm going to solve for this volume of hydrogen gas. And because they say I'm at STP, and since it's a gas, that means I can use the 22.7 cubic decimeters equals 1 mole. So that from part 2, we can use on this one because it's a gas at STP. We could not use that on the first one because this was a solution. So for this one, I'm going to start, pretty much the same way. I'm going to start with my 5 grams of magnesium. I still need magnesium's molar mass to convert to moles. And then I still need a molar ratio. However, now the molar ratio is going to be from magnesium to this product of hydrogen gas. Neither of them have a coefficient, so they are both 1. So 1 mole of magnesium to 1 mole of hydrogen gas. And then the last one, since this is gas and they told me it's STP, that means that I can use that molar volume. So any gas at STP is going to be that 22.7 cubic decimeters. And so again, this one I would set it up in my calculator, and I would do 5 divided by 24.31, and then times 22.7, because everything else is ones, and so those will not affect the number of the answer. So 5 divided by 24.31, and then I'm going to multiply by 22.7. And again, I want to have 3 significant figures because of this 5.00. And so my answer would be 4.67 cubic decimeters of hydrogen gas. And that's it. So 2 and 3 on here are pretty similar to that. You're going to be using the concentrations like we did this one for HCl as part of the conversion factor for the calculations. If it asks you about a gas at STP, you can use the 22.7 cubic decimeters, but if it doesn't ask you about a gas, if it only asks you about a solution, then you're going to have to use the concentration and not that 22.7. So hopefully you guys can work through these and get your questions turned in on time. If you guys have any questions, let me know during our live class, or you can always message me on Remind.